Okay, so as you can see from the title of Chapter 5, it sounds very scary. Logarithmic, exponential, and other transcendental functions. You know what logarithms are, yes? You know what exponentials are, yes? Do you know what transcendental functions are? No, they're scary. Similar to yesterday, what we're going to do is start with a little bit of practice, because I think some of you can stand to have some practice, since it's been like 2 weeks since we've done this stuff. But today we're going to talk about natural log eventually, at some point, and we're going to talk about how to take the derivative of the natural log, but that comes later. So, like I said, we're going to talk about the natural log function. We're going to talk about the number e. You've seen that before, yes? Beautiful. And we're going to talk about how to take the derivative of those things. Okay, so here's the review. Let's start with a very simple problem. Solve that, please. Without your calculators. Do it by hand. Nobody wants to be Phil's friend? You can be okay over here by yourself? Yeah, okay. You have no excuse. How are we doing? That table's a train wreck. Is that new?
Yes.
Is it real?
Yeah.
I can see it's also being.
Yeah.
Yeah, that's what. All right, wait, hold on. Let's back up. I know it's been 2 weeks, but why are we having such big problems? All right, get out your calculators then. And the FN is that thing. Wait, how do you do it? Yes, there you go. Yes. Okay, so you all got an answer, right?
Yeah.
What is it? 1 point blah, 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 something. Okay, so what does that mean? What is that thing that that's not even an equation? What does that expression represent? Area under the curve from 1 to 4 below the function 1 over x. Okay, so you should be able to do that, yes? The calculator's telling you there's an answer. If you want a picture, there's the graph. You can see from 1 to 4 there is a positive area under there. Why can't you do the antiderivative? What was the problem? Drew?
When you do the antiderivative of x to -1, you just get x to 0.
Okay, hold on 1 second. So I'm going to do the integral from 1 to 4 of x to the -1 dx. That's a good start. How do I do that?
You just increase the exponent by 1.
-1 plus 1 is 0?
Yeah.
Math guy.
Yeah. And then
Is that a problem? Excuse me, is that a problem?
Yeah.
No. What's x to the 0?
Well, it's 1.
1, okay.
But then you can't plug in the 4 and 1 to find it.
Well, hold on, we're not done.
Oh, yeah, then you also have to divide by 0.
Why divide by 0?
Because you divide by the exponent.
Right, so here comes the review. If I'm taking the antiderivative of x squared, raise the exponent by 1, multiply by the reciprocal of that exponent, plus c. So the problem comes in here. The reciprocal of 0 is 1 over 0, and that makes no sense. But do you see the problem here? that equation that Drew just talked us through doesn't work. But you know there must be an answer. There's a shaded region there. Your calculator, which is smarter than all of us, tells us there's an answer. Right? You can see it. It's this, it's this stuff. From here to here. It's a positive answer. It's above the x-axis, all that other fun stuff. How do we deal with this? And so the way we deal with it is we create a whole new concept, and that concept is the natural log. And you probably never talked about this because you haven't had the calculus. In pre-calc and advanced algebra, you dealt with natural logs all the time. Log base 6, log base e, all those other fun things. You talked about logs, and in particular natural log, but I'm guessing you probably never talked about where the natural log came from. It's a button on your calculator, you can do all these calculations, but this is the derivation of it. Since that doesn't work, then somebody says, okay, hold on, we're just going to define it differently. We're going to define the natural log as the area under that particular function from 1 to some number. So just for giggles, on your calculator, take the natural log of 4. What do you get? Say again? Well, what's more important is that it's the same value, right? So the natural log is now being defined as the area under the curve of 1 over x from 1 to whatever number you get. That's a sneaky way of getting around the whole concept that that is undoable. That being the antiderivative is undoable based on our skill set. So they said, whoever they is, said I can't do that, so I'm just going to call it something special and move on from there. And the calculator is already programmed to work around that problem. Questions? You understanding that now? So it adds a new twist into what a natural log is. Now you know where they come from. Whether you cared or not, that's where natural log comes from. By the way, you all know that natural log is log base e, yes? All right, good. I just wanted to make sure we're on the same page here. Thankfully, your pre-calc teacher did something correctly. Right, so here's a log function. Here's a natural log function. I'm sure you know what this looks like. It passes through the point 1, 0. And then there's a bunch of other information in there. The domain goes from 0 to infinity. The range is from negative infinity to infinity. It is continuous. It's increasing and it's 1 to 1. It's also concave down. That's probably review for you. Yes? Good. Here's some stuff that you need to, this is also review, pre-calc advanced algebra stuff. The natural log of 1 is 0. However, the question I want to know is, why is it 0? Explain, or elaborate.
Go from 1 to 1, so they can't be any area under it.
Very good. The natural log of a product is the sum of the natural logs. The natural log of an exponent, you can move the exponent out in front. And the natural log of a the natural log of a quotient is the difference of the natural logs. And again, I'm sure you remember all of this from pre-calc. Good. No sarcasm in that statement at all. Okay, we good? All right, let's do some more review. You don't have to write these down. This is just examples of what I showed you on the previous slide. So the natural log of 10/9 is the natural log of 10 minus the natural log of 9. The natural log of the square root of 3x plus 2. Well, the square root is the same thing as raising it to the 1/2, so raise it to the 1/2 and then move the 1/2 out in front. Can't do anything with the stuff in parentheses, because notice there's no formula for the natural log of a sum. It's only the natural log of a product or the natural log of a difference. We can do a couple things. Step 1 would be to turn the quotient into a difference, and then we can also take that first part and turn it into a sum. So if we break it down into that, you get 3 different natural logs from the original first natural log. And you'll be practicing doing both of those, taking one natural log and breaking it into parts, or taking the parts and putting it back together. In other words, doing those backwards. Most of the time, however, we're going to break them down. We're working towards a new way to take derivatives for very complex problems that simplify your life and allow you to do it very easily. I think we'll do that tomorrow. A little teaser. Okay, the number E. Anybody know what it is? Who's got a $20 bill? Maybe?
I got one.
Anybody have a 20? I got 20? Okay. All right, so here's how you remember E. Has anybody seen this before? All right, here we go. What is this? $20 bill. Who's on the $20 bill? Andrew Jackson. Do you know which president he was? The 7th. Do you know what? How do you know this?
No.
Freak show.
Bush.
Do you know? All right, let's see. Do you know what year he was elected?
After 1800.
Very good.
12?
1828.
Oh, 16 years ago.
He ran for 2 terms, right? 1828. Now we do some math. I'm doing some more math. A goose. Okay, remembering back to your fond years in geometry, you would shut up. Who said that, by the way? It wasn't you, was it? Better not be. Okay, what is this? What kind of triangle? Isosceles. Right triangle, also known as? No. What, you don't remember what? I heard somebody say it. 45, 45, 90. Okay. Watch carefully. It's a $20 bill. Andrew Jackson is the 7th president. He was elected in 1828. He ran for 2 terms. When you fold this up, you get a 45, 90, 45 triangle. How could you forget it now? 2.7, 1828, 1828, 459045. Find the button on your calculator. There's an E button on your calculator. Find it.
I found it.
Beautiful.
Wow.
What's the calculator say?
2.718.
Stops at 8. Okay, good. So this is more helpful because it takes it out further. Great party trick. Impress your friends. So now you know, similar to the natural log with what you did in pre-calc last year, you know how to work with the natural log. In this case, you know what E is now. It's a number. Remember, it's a constant, so it's like pi. So what would be the derivative of E? 0, correct, very good. Okay. You know what E is approximately. E continues, it's irrational, but that's enough to get you out to 2, 4, 6, 8, 10, 12, 14, 15 decimal places. But where does it come from? And you probably have no idea, do you? Well, I'm going to tell you. Because it involves calculus, which is probably why you've never seen it before. Okay. So that's how E is defined. We take that stuff that we did with the graph of 1 over x, and we slide from 1 over until we get to a number. What that number is irrelevant for a second. We slide over until the area of that pink region is equal to 1. And when that happens, where do we end up? We end up at that number, 2.71828, 1828, and then they cheated by rounding, but it would be 45904. Okay. So it's the area under the curve of 1 over x. having a value of 1. So there's a lot of information in those first couple slides. You found out where natural log comes from, and now you found out where E comes from. I know you're so excited. So there's the official definition. The natural log of E, which is the integral from 1 to E of 1 over t dt, must be equal to 1 in order to get that number.
You've known yourself your whole life. You don't know anything about yourself.
I know a lot about myself, but there's nothing important.
Okay. Jacob? You like traveling?
Good? No? Now good? Yeah. Use your calculator. Check to make sure you're doing this right. I don't know how you could screw this up, but just for giggles. Let's talk more importantly about what does the natural log of 2 mean from a calculus standpoint. Be more specific.
It's the area under the 1 over x 1, 2.
Perfect. Couldn't have said it better myself. Natural log of 32. So as the number gets bigger, the natural log should get bigger because you're moving further down that x-axis. I don't have it in here, but just for giggles, take the natural log of 1,000,000. Okay, so it's a bigger number. Why is the natural log of 0.1 a negative number? Elaborate. You're on the right track. Go.
Since the top is more than the bottom.
Good. Which is what you were saying, you're going the other direction. Since 0.1 is to the left of 1, when we set up the integral from 1 to 0.1, okay, so what does this mean? That means the integral from 1 to 0.1 of 1 over x dx, whoops, dx. As Luke mentioned, the upper limit of integration must always be bigger. So this doesn't work, we need to flip it. This is the same thing as 0.1 to 1 of 1 over x dx. However, as he mentioned, anytime you flip the limits of integration, you have to put a minus sign in front of it. Beautiful. Go back. Okay. The next thing is the derivative of the natural log. I don't know how to do that, but it's really easy. You just got one simple thing to remember, which I'll get to in a second. Okay, so you could read that, blah, blah, blah. First part of your clause definition, natural log. The second part of the chain rule for the, okay, who cares? If we go backwards, so in that last slide, we've got this. Let me get rid of this. We'll go back just the basic formula here. So we'll go away and come back to here. And we say that's x. This should be a t. Just trying to keep things legitimate here. So t dt, and that's equal to the natural log of x. Okay, that's by definition. So how do I get rid of the integral? Take the derivative of both sides. So I'd like to know, as it says in the next slide, I want to know what the derivative of the natural log of x is. So simple rule of algebra, whatever you do to one side of the equation, you have to do the other. So I'm going to end up taking the derivative of the right-hand side. What's the derivative of an integral? It cancels out, right? This is the second part of the fundamental theorem of calculus. T's become x's. Chain on the derivative of the top function. t's become x's, chain on the derivative of the top function, but the derivative of the top function is 1. So we get that. What if it's not t? What if it's a whole different function? Like x cubed minus 7. Well, we would do some magic and use the u substitution. This u, that t would become a u, this would be du, and this would be u up there. Go through the same process. We would get 1 over u, but you have to chain on the derivative of that top function, which is u prime. Having done all that, we get to this nice little slide there that gives you both scenarios. You're going to use number 2 99% of the time. And in fact, I would say you're going to use number 2 100% of the time, because if 1 over x comes up, you're smart enough to know that the derivative of x is 1. That's what you want. U prime over u. What's the derivative of natural log of u? U prime over u. Just to keep things simple, using the KISS method, what does u prime over u mean? Yeah, take the derivative of the function and put it over itself. Don't make this more difficult than it has to be. Please. Ready? Whoops. What's the derivative of the natural log of 2x? Say again? Nope. Anybody else? No? 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 There you go. Keep it simple, stupid. Nope. 1 over x. Who said that? Explain. Because you just heard 4 people go, why?
I did the derivative of 2x, which is 2 over 2x, and I simplified it 1 over x.
Hot diggity. Again, KISS method. U prime over u. What's u prime? As Ashton said, u prime is 2. What's u? 2x. 2 over 2x. It's just 1 over x. Keep it simple. Number B. Which one person got it next time? Who's talking? What do you got? Why did you just refer to yourself in the third person? It's freaking Grady out.
Is it 2x over x squared plus 1?
Hold on. Is it 2x over x squared plus 1?
Yeah.
Well, let's click and find out, shall we? No.
No plus c?
No plus c. Because it's a derivative, not an integral. There you go. Well done. How could we make it more interesting?
Make it a fraction.
Ooh, a front. I didn't think of that. Trigonometry. Yeah, yeah. To be honest, I don't remember what I did, so this will be exciting for all of us. Ooh. Ooh. Product rule. Come on now. So notice that that's not a u prime over u right away. It's a product rule between 2 functions, x and the natural log of x. So if you'll recall, because it was so long ago, the first times the derivative of the second plus the second times the derivative of the first.
Okay.
What's the derivative of natural log? We just did that. No, it's not 1.
Natural log of 1 is 0.
It's 1 over x. What's the what's the derivative of x? That's 1. We get that, which simplifies to 1 plus the natural log of x. What else could we do? Well, we did a product rule.
Oh,
We could do a chain rule. We could do a quotient rule. We could combine a quotient rule with trigonometry. Ask and you shall receive. Chain rule. Okay, so before we talk about how this one is solved, one thing you need to remember, which is very common, is as soon as somebody sees a natural log and a derivative, they all of a sudden just go to u prime over u. Okay? That's not the case in C and D. The derivative of natural log is a component of solving the problem, but it's not all we need to do. So notice that in part D we have something raised to the third power. Well, how do you take the derivative of something raised to the third power? You bring the 3 down, reduce it by 1. That's the first part of that answer. And then you chain on the derivative of the thing inside. Well, the thing inside happens to be a natural log. And we've already talked about the derivative of the natural log being 1 over x. So that becomes that. And no, you cannot cancel the x's. Don't do that.
I probably will.
Then you'll get a come on man for that. I think we should probably stop here. Because we're going to get into this thing called called logarithmic differentiation, which will allow us to take the derivative of big scary formulas using what we just learned. However, based on some of the way the discussions went today, we might want to practice that previous stuff before we dive into this bad boy. So we'll stop there for today and pick up where we left off tomorrow with logarithmic differentiation, which isn't that nasty, and in fact you'll find it very helpful for complicated derivatives. Questions? Yes, Drew?
What happened to my 20?
You're 20. What 20? I do it every year. In 3 years, I've managed to keep the 20 till the end of the day, and they're always standing at the door of 8th period. Do you have my $20 bill? You're smarter than the average bear, Drew.